Picture this. Every single second, the top of our atmosphere absorbs a flood of energy equivalent to hundreds of thousands of nuclear power plants running at once. That energy left the sun 8 minutes earlier, crossed 93 million miles of empty space, and now it's slamming into clouds, oceans, ice sheets, and cities, all at the same instant, all across the planet. Some of it bounces straight back into space, gone in a fraction of a second. The rest gets absorbed, turns into heat, drives the wind, evaporates water, and powers every living thing on the planet, from the smallest plankton in the open ocean to the largest storm system spinning across a continent. Eventually, as invisible infrared radiation, Earth has to send that energy back out into the darkness of space, completing a cycle that has repeated itself uninterrupted for over 4 billion years. That exchange, this constant back and forth between our planet and the cosmos, is the reason oceans stay liquid, the reason climate stays stable, the reason life exists at all, rather than existing on a frozen rock or a scorched one. But what happens if that mechanism starts to break down, quietly, gradually, in ways too subtle for any one person to notice from the ground? What if Earth keeps receiving energy just as reliably as it always has, but slowly loses its ability to give it back? This is not a film about heat waves. It's not a film about weather, and it's certainly not another film about the climate crisis the way you've heard it described 100 times before. This is an investigation into the single most fundamental process that determines the temperature of our planet. The quiet, invisible negotiation between sunlight and space that has been running, largely unnoticed, since Earth first formed. And over the last 2 decades, scientists have been picking up signals that this negotiation is shifting faster than any model predicted. Let's start from the beginning. How Earth's energy balance actually works, and why the satellites watching over it recently caught something that caught even veteran climate scientists off guard. Something that took years to fully confirm, and that is still reshaping how researchers think about the planet's future. Every object in the universe with a temperature above absolute zero radiates energy. Your body does it. A cup of coffee does it. A distant star does it. Earth is no exception. The sun heats the planet, and the planet radiates that heat back into space as infrared light, a wavelength invisible to human eyes, but perfectly visible to specialized instruments built specifically to see it. If the amount of solar energy absorbed exactly matched the amount radiated back out, Earth's temperature would stay rock steady for millennia, neither warming nor cooling on any meaningful timescale. That's the equilibrium that keeps climate stable, the quiet arithmetic underlying every season, every ocean current, every snowfall. But equilibrium isn't a given, and it never has been. It's a fragile balance shaped by dozens of variables: cloud cover, ice extent, greenhouse gas concentrations, atmospheric dust and aerosols, ocean temperature, even the tilt of the planet's orbit over long timescales. Shift any one of those, and the balance tips, sometimes by a fraction of a degree, sometimes by much more. Scientists call the gap between incoming and outgoing energy Earth's radiative imbalance, or Earth's energy imbalance. It's measured in watts per square meter, the amount of extra energy landing on every square meter of the planet's surface, day and night, summer and winter. The number sounds almost too small to matter, a little over half a watt per square meter, roughly the output of a single dim light bulb spread over an area the size of a dinner table. But multiply that across the entire surface of Earth, more than 197 million square miles of ocean, ice, forest, and desert, and you get a staggering amount of energy accumulating inside the system every single second. Energy with nowhere else to go but into the ocean, the ice, and the air. For most of scientific history, this imbalance was almost impossible to measure directly. The signal was simply too faint, buried under a mountain of noise from shifting clouds, drifting aerosols, and ordinary seasonal swings that dwarfed the underlying trend. That changed with a satellite mission that modern climate science simply couldn't function without. CERES, Clouds and the Earth's Radiant Energy System. The first CERES instrument, launched in the late 1990s, aboard a satellite built to track tropical rainfall, almost as an afterthought to its main mission. Since then, an entire family of CERES sensors has taken up orbit aboard NASA's Terra and Aqua satellites, along with the newer Suomi NPP and NOAA 20 platforms, quietly building one of the longest, unbroken climate records ever assembled. Think of an orbital outpost bristling with ultra-precise sensors sweeping over the planet in wide bands, capable of detecting the faintest shifts in the energy flowing in and out below. These instruments continuously measure how much sunlight bounces off clouds, ice, deserts, and ocean, and how much heat Earth radiates back as infrared, orbit after orbit, day after day, year after year. More than 25 years of continuous observation have made CERES the gold standard of climate measurement, the closest thing humanity has ever built to a thermostat for the entire planet. And CERES data delivered one of the most unsettling and genuinely fascinating discoveries of the last few years, one that would take an entirely independent line of evidence to confirm before anyone was willing to fully believe it. In 2021, a team led by climate scientist Norman Loeb published a study that forced the climate community to stop and rethink its own assumptions. The kind of paper that gets circulated and reread across an entire field within weeks. According to their satellite analysis, Earth's energy imbalance, the surplus of absorbed energy over radiated energy, had roughly doubled in just 14 years, from 2005 to 2019. A doubling isn't a slow, gradual drift. It's a sharp jump, and one that previous generation climate models simply hadn't predicted at that pace. If you'd told a climatologist 20 years ago that the planet's energy imbalance would double in under a decade and a half, they'd have called it an overly pessimistic scenario, the kind of number you'd expect from a worst-case projection, not from an actual measurement pulled straight out of the data. To rule out instrument error, scientists turned to a completely independent source of data, one that had nothing to do with satellites at all. A global fleet of autonomous ocean floats called Argo. Thousands of these floats drift through every ocean on Earth, silently diving to a depth of roughly 6,500 feet and back on their own schedule, measuring temperature and salinity at every level along the way. Since more than 90% of the excess energy the planet accumulates ends up in the ocean, changes in ocean heat content should either confirm or contradict what the satellites were seeing from orbit, two completely different vantage points on the exact same question. They matched. Whether scientists looked at Earth from orbit hundreds of miles up, or measured water temperature in the depths of the Pacific and Atlantic, thousands of feet down, both methods told the exact same story. The planet is accumulating energy faster than it used to, and it isn't a fluke of one instrument or one dataset. That discovery kicked off dozens of follow-up studies trying to figure out what was actually driving the acceleration. each one approaching the question from a slightly different angle. And one of the most surprising conclusions was that the culprit wasn't simply rising carbon dioxide, as you might expect walking into this story cold. To understand what's happening, you need to understand albedo, a surface's ability to reflect sunlight back into space rather than absorbing it. Fresh snow reflects nearly 90% of the light that hits it, almost like a mirror. The dark ocean, by contrast, reflects only a few percent, swallowing nearly all the sunlight that reaches it. Clouds sit somewhere in between, reflecting a significant share of solar radiation depending on their type, altitude, and density. Earth's overall albedo averages around 30%. That's how much sunlight the planet bounces back into space without absorbing it at all. A number that sounds abstract until you realize how much depends on it staying roughly constant. And here's where the story gets interesting. Satellite observations show that Earth's albedo has been quietly declining. The planet is getting slightly darker, not in any visible sense you'd notice looking up at the sky, but in its capacity to reflect sunlight back out, which means it's absorbing more energy than before, even before you factor in rising greenhouse gases. That's a genuinely surprising twist, because for years, the public conversation around warming barely mentioned reflectivity at all. Why is that happening? The answer turned out to be more complicated than anyone expected, made up of several interlocking processes, each one worth unpacking on its own, and each one, on its own, capable of reshaping how we think about a warming planet. Start with the poles, where change is happening faster than anywhere else on the planet. Climatologists call it polar amplification. The Arctic is warming several times faster than the global average. By some estimates, nearly 4 times as fast. A difference stark enough to reshape entire ecosystems within a couple of decades. The reason lies in what's known as the ice-albedo feedback loop. Sea ice reflects sunlight. Open, dark ocean water absorbs it. When ice melts, the reflective surface shrinks. The ocean absorbs more heat, and the ice melts even faster. It's a self-reinforcing cycle, one that feeds on itself year after year. And it's why shrinking Arctic sea ice matters not just for polar bears and coastal ecosystems, but for the energy balance of the entire planet. Satellite records going back to the early 1980s show a steady decline in summer Arctic sea ice, frame after frame, revealing more open water where solid white ice used to stretch to the horizon. The thickness data is especially telling. Old, multi-year ice built up over decades, ice that has survived summer after summer, is steadily being replaced by thinner, seasonal ice that melts and reforms every year, leaving the ice pack more fragile and more vulnerable to further change. Antarctica, curiously, behaves differently, and that's become one of the great puzzles in polar science. Where Arctic ice loss has followed a fairly predictable, almost linear trajectory, Antarctic sea ice showed a much more erratic pattern for decades, expanding some years, shrinking others, before suddenly plunging to record lows starting in the mid-2020s. A reversal so abrupt, it caught even specialists who had spent entire careers studying the region off guard. Scientists are still debating what's driving that shift. Changes in ocean currents, wind patterns, deep water temperatures, or some combination of all three. It's one of those questions where no clear consensus has emerged yet, and honest science admits it. Antarctic ice dynamics are far less understood than their Arctic counterpart. But ice isn't the only reason the planet is darkening. The second major factor involves something that sounds paradoxical at first, almost counterintuitive: cleaner air. Over recent decades, many countries, particularly across East Asia, and especially the global shipping industry, have adopted strict rules to cut sulfur emissions, the same particles responsible for smog, acid rain, and serious harm to human health. These measures are entirely justified from a public health standpoint, full stop. Clean air saves millions of lives every year by reducing respiratory and cardiovascular disease, and nobody in the scientific community disputes that. But those same sulfate aerosols had a quiet side effect that almost nobody outside a narrow circle of atmospheric specialists ever thought about. They reflected sunlight back into space on their own, and they helped form denser, more reflective clouds by giving water vapor more surfaces to condense around. Scientists call this aerosol cooling, and for decades, without most of the public ever realizing it, it partially masked the true scale of greenhouse warming happening underneath. The shipping industry offers a particularly striking example. In 2020, new International Maritime Organization rules slashed the allowable sulfur content in ship fuel almost overnight. The goal was to protect coastal populations and clean up the air over major shipping lanes, a genuine public health win. But researchers noticed something unexpected. In the very ocean corridors where high-sulfur ships used to leave behind long, bright streaks of cloud trailing behind them, so-called ship tracks, visible even from space, cloud cover became thinner and less reflective almost as soon as the new rules took effect. Some studies link that shift directly to part of the previously unexplained acceleration of warming in the North Atlantic. It's a genuine paradox, one that even seasoned climate scientists find striking. Decisions that were absolutely right for public health simultaneously pulled back a kind of veil that had been partially masking the intensity of the greenhouse effect all along. That's why many climate scientists are careful to describe falling aerosol pollution not as a new cause of warming in its own right, but as the unmasking of a process that had already been underway for decades, hidden in plain sight behind a haze of industrial pollution. The third factor is clouds themselves, arguably the most complex and least understood piece of the whole picture, and the one climate scientists spend the most time arguing about at conferences. Clouds are a strangely two-faced part of the climate system. On one hand, they reflect sunlight and cool the planet, acting like a sunscreen. On the other, they trap outgoing heat radiation like a blanket, warming it. The net effect depends on cloud type, altitude, density, and location, which is exactly why clouds have resisted easy modeling for decades. Low, thick clouds over the ocean generally cool the planet by reflecting sunlight straight back into space, acting almost like a sunshade over vast stretches of blue water. High, wispy cirrus clouds tend to do the opposite, trapping heat instead. Shifts in global atmospheric circulation driven by warming are reducing low, reflective cloud cover in certain regions, especially subtropical zones over the open ocean, exactly the places where that sunshade effect matters most. Scientists call this the low cloud feedback, and previous generation climate models systematically underestimated its strength. At a gathering of leading climate scientists at the Max Planck Institute for Meteorology in spring 2026, more than 40 researchers from Asia, Europe, and North America sat down together to go through the entire CERES record from 2005 through 2024 in painstaking detail. Their conclusions were remarkably specific. Earth's energy imbalance had grown by roughly 0.3 to 0.5 watts per square meter per decade. And that growth was driven primarily by the short-wave side of the spectrum, reflected sunlight, rather than the long-wave infrared side. In other words, the problem wasn't so much that Earth had gotten worse at radiating heat back out. It was that Earth had started absorbing more sunlight in the first place, thanks to shrinking ice and thinning reflective cloud cover. That distinction matters enormously, because it shifts the entire focus of the story away from a single familiar villain. For years, the public understanding of warming boiled down to one simple idea. Greenhouse gases trap heat like a blanket and won't let it escape back into space. That's true, and the role of carbon dioxide, methane, and other greenhouse gases remains fundamental and scientifically ironclad. Nothing about that has changed, and nothing in this new research contradicts it. But recent data shows that a significant share of the acceleration in Earth's energy imbalance comes from something different. Changes in how much sunlight gets absorbed in the first place. The shortwave side of the ledger, not just the longwave side everyone already knew about. There's one more fundamental piece of this puzzle worth pausing on: water vapor. It's the most powerful greenhouse gas in the atmosphere by far. But unlike carbon dioxide, its concentration isn't directly controlled by human activity. Instead, water vapor acts as an amplifier. The warmer the atmosphere gets, the more moisture it can hold. And that extra moisture traps even more heat, which lets the atmosphere hold even more moisture still. This feedback has been known to climatologists for well over a century, built into the most basic physics calculations dating back to the 1800s. But combined with shifting cloud patterns and declining albedo, it adds another layer to an energy imbalance that resists being broken down into single, isolated causes. Now to the question of where all this excess energy actually goes. Because the ocean isn't some passive holding tank quietly absorbing whatever falls into it. It's an active, staggeringly complex participant in the entire climate system. One that shapes weather, storms, and even the fate of the ice caps thousands of miles away. Picture the ocean as a colossal thermal battery, stretching miles down into darkness, holding far more energy than most people ever consider when they think about a warming planet. Water has an enormous heat capacity. It takes far more energy to raise its temperature than it does to warm the same volume of air or land. That's precisely why more than 90% of the excess energy the planet accumulates ends up in the ocean depths, quietly, invisibly, rather than in the atmosphere we actually feel against our skin day to day. Data from the Argo float network, gathered over more than 2 decades of continuous, uninterrupted operation, shows a steady and virtually undeniable rise in ocean heat content across nearly every depth, from the sun-warmed surface down through the cold, dark, intermediate layers hundreds of feet below. One of the clearest signs of that accumulating heat is the rise of marine heat waves, stretches of abnormally high sea surface temperature that can last for weeks or even months, spreading across areas the size of entire continents, invisible from the surface, but unmistakable to anything living beneath it, from tiny plankton to full-grown whales. These events have shown up in the North Pacific, the Atlantic, the Mediterranean, and the waters around Australia. Marine heat waves devastate coral reefs, triggering mass bleaching events that turn vibrant reef systems ghostly white almost overnight, shift the migration routes of marine species that have followed the same paths for generations, and disrupt fisheries and coastal economies that depend on those waters staying within a narrow, predictable temperature range. Notably, some regions of the northeastern Pacific and Atlantic have warmed faster than almost anywhere else on the planet. Faster even than many land-based hotspots that tend to dominate the headlines and the news cycle, which has pushed researchers to dig deeper into the local circulation patterns that might be amplifying heat accumulation in those specific zones. Patterns that don't show up anywhere near as strongly just a few hundred miles away. Let's take a detour to atmospheric circulation, the fast-moving air currents that determine where it's sunny, where it's cloudy, where deserts form, and where rainforests thrive. We're talking about the jet streams, narrow, high-speed bands of air roughly 6 miles up, tearing along at well over 100 miles an hour, encircling the planet at mid and high latitudes. The temperature difference between the equator and the poles is what powers the jet streams, the way a pressure gradient drives any current of air or water. But because the Arctic is warming so much faster than the equator, that temperature gradient is shrinking, and the behavior of the jet streams is shifting along with it. Some researchers link the weakening and increasingly wavy path of the jet streams to more frequent, more persistent weather extremes, prolonged heat in some regions, prolonged rain in others. This is a separate, genuinely difficult area of research, one where scientific consensus is far less settled than it is on the basic fact of a growing energy imbalance. Still, the connection between polar amplification, atmospheric circulation, and regional weather extremes remains one of the most actively studied topics in atmospheric science today. Back to the ocean, because this is arguably where the biggest, least visible part of the story is unfolding. Picture a research vessel out in the middle of the North Atlantic, gray swells rolling under a low sky, its crew lowering another autonomous Argo float over the side and watching it disappear beneath the surface. The instrument will sink to roughly 1.25 miles down, drift silently with the current for about 10 days, then rise back to the surface on its own, recording a full profile of temperature and salinity at every depth along the way, before beaming the data up to a satellite and into a global database available to scientists everywhere, free of charge, within hours. Thanks to a network of nearly 4,000 of these floats scattered across every ocean on the planet, quietly diving and surfacing on their own around the clock, scientists have, for the first time in history, been able to continuously track heat content throughout the entire water column, not just at the surface, which is all satellites alone can see from orbit. And that data confirms something important. Heat isn't just piling up near the surface. It's accumulating hundreds of feet down, too, which means the ocean is absorbing energy at a depth far greater than surface temperature alone would ever suggest. There's also the question of how the ocean redistributes all that stored heat across the planet. Ocean currents work like a planet-scale heating and cooling system, carrying warm water from the tropics toward the poles along the surface and sending cooler, denser water back along the depths. The Atlantic meridional overturning circulation, the broader system of currents that includes the familiar Gulf Stream, the current that keeps Western Europe far milder than its latitude would otherwise suggest, has drawn intense scrutiny in recent years over possible signs of slowdown. Here it's important to stay scientifically careful. Measurements of this circulation's speed and stability are limited by historical standards. Direct continuous monitoring is relatively recent, and while paleoclimate evidence shows this kind of circulation can shift abruptly in the deep past, current observations don't yet support a confident conclusion about how fast, or how likely, such a shift really is in the coming decades. It's another vivid example of an open scientific question. one where intriguing data runs up against a genuine shortage of long-term observation. There's a natural counterpart to all this satellite and ocean data: the natural events capable of temporarily masking or amplifying the underlying trend, which is exactly why climatologists rely so heavily on understanding them before drawing conclusions from any single data point. Major volcanic eruptions are among the most dramatic examples, capable of reshaping the global energy budget for years at a stretch. Mount Pinatubo's eruption in the Philippines in 1991 blasted a colossal quantity of sulfate aerosols high into the stratosphere, measurably cooling the entire planet for several years afterward by reflecting sunlight back into space before it ever reached the lower atmosphere. Global temperatures actually dipped in the years that followed, a brief, natural counterpoint to the long-term warming trend. Events like these serve as natural experiments, letting scientists test how accurately climate models can reproduce the system's response to a sudden shift in atmospheric aerosols. Another natural factor operating on shorter timescales is the El Niño-La Niña cycle in the tropical Pacific, a back-and-forth rhythm that has shaped weather patterns worldwide for as long as records exist. During El Niño, huge volumes of warm water that have been building up beneath the surface rise up in the eastern Pacific, releasing stored heat into the atmosphere and temporarily pushing up the global average air temperature. During La Niña, the reverse happens, and some of that heat temporarily sinks back down into the ocean, out of sight. That's why individual record-hot years so often coincide with El Niño conditions, and it's exactly why climatologists always factor this natural variability into their analysis of long-term energy imbalance trends, rather than reading too much into any single year. Given all this natural variability constantly nudging the numbers up and down, it becomes clear why scientists put so much weight on long-term, multi-decade satellite records, rather than any single headline-grabbing year. One unusually warm year, driven by a combination of El Niño and a random dip in regional cloud cover, doesn't prove anything on its own. It's noise, however dramatic it might feel in the moment. But a sustained trend, observed consistently over 2 full decades and independently confirmed by both satellite measurements from orbit and ocean data collected from below the surface, is solid scientific ground for drawing real conclusions. Given the discovery of an accelerating energy imbalance, scientists have also started discussing what measures, beyond the obvious and most fundamental solution of cutting greenhouse gas emissions, could theoretically influence the process on a shorter timescale, buying the planet some breathing room while deeper decarbonization plays out over decades. Some research groups, mostly in academic settings, have begun studying the theoretical possibility of artificially boosting Earth's reflectivity, an area the scientific literature calls solar radiation management. Proposed ideas range from the modest to the almost science-fictional, releasing reflective particles into the stratosphere to mimic the cooling effect of a volcanic eruption, brightening marine clouds by spraying fine seawater mist to increase their reflectivity, and even hypothetical proposals to place reflective shades in orbit between Earth and the Sun, blocking a tiny fraction of incoming sunlight before it ever reaches the atmosphere. It's worth emphasizing that the overwhelming majority of these proposals remain firmly in the realm of theoretical study and small, controlled experiments, not practical policy anyone is close to implementing at scale. The scientific community treats these ideas with substantial caution, since artificially altering the planet's reflectivity could affect regional weather patterns, rainfall, and other elements of the climate system in ways that aren't yet well understood. The kind of large-scale intervention that could easily trade one poorly understood problem for another. These studies are another vivid example of how actively modern science is working to understand the mechanics of Earth's energy balance, while maintaining real caution about intervening in such a complex system. Scientific honesty requires acknowledging the limits of current knowledge, even when that's less satisfying than a tidy, definitive answer. Researchers working with CERES and Argo data routinely publish not just confirmed conclusions, but explicit lists of open questions requiring further study, a kind of public accounting of what remains unknown. That willingness to admit uncertainty, paired with a disciplined, methodical search for answers, is exactly what separates serious science from the sensational claims that sometimes circulate in popular media. Before moving on, it's worth grounding all this in specific numbers, because these figures underpin every calculation climate scientists make. Atmospheric carbon dioxide, which held remarkably steady around 280 parts per million for millennia before the industrial era, now exceeds 420 parts per million, a rise confirmed by dozens of independent monitoring stations scattered across the globe, from the summit of Hawaii's Mauna Loa volcano to remote research outposts in Antarctica, all measuring the same steady climb. Methane, far shorter-lived in the atmosphere, but far more potent per unit of mass, is also climbing, and the pace of that increase in recent years has drawn particular interest from researchers trying to untangle how much comes from human activity versus natural sources like wetlands and thawing permafrost. Each of these gases contributes to what climatologists call radiative forcing, the additional energy trapped in the climate system due to changes in atmospheric composition compared to the pre-industrial baseline, before humans began altering the chemistry of the air at scale. The accumulated radiative forcing from all greenhouse gases combined forms the fundamental long-wave component of the energy imbalance already discussed, the part of the story that's been understood the longest. But as shown, over the last 2 decades, a second, less expected component has been layered on top of that long-known baseline, the shortwave component, tied directly to Earth's declining albedo. The combination of these two components, a steadily rising radiative forcing from greenhouse gases building up over a century and a half, plus a faster-moving, more recently discovered contribution from declining albedo, produces exactly the picture of accelerating energy imbalance that caught the climate community so off guard in the early 2020s, and that is still being pieced together today. It's worth returning to the geography of these changes and looking at a few specific regions where these processes show up most vividly. The kind of places a documentary film crew would find an extraordinarily rich visual canvas, each one telling a slightly different piece of the same larger story. Start with the Svalbard archipelago in the Norwegian Arctic, a scatter of glaciated islands well above the Arctic Circle and one of the fastest warming places on the entire planet. Weather stations there have recorded warming rates that, in some years, run 6 to 7 times faster than the global average, a pace that has visibly reshaped the local landscape within a single human generation. The cause is the same ice albedo feedback described earlier. Shrinking sea ice around the archipelago exposes ever larger patches of dark ocean water, which absorbs solar energy instead of reflecting it back into space. Shift to the opposite end of the planet, the Ross Sea off the coast of Antarctica, a stretch of ice shelf and open water that expedition ships have to navigate carefully even in the best conditions, where sea ice hit record lows in the mid-2020s, the lowest levels of the entire satellite record dating back to the late 1970s. That's especially striking because for most of the preceding decades, Antarctic sea ice extent had been relatively stable or even slightly increasing, in stark contrast to the steadily shrinking Arctic. That sharp reversal has become one of the great puzzles in polar climatology, and research expeditions aboard specialized icebreakers, pushing through pack ice in brutal cold, continue collecting data, trying to understand what's driving the shift. A reorganization of ocean currents, changing deep water temperatures flowing out from beneath the ice shelves, or some combination of factors still being untangled. Another telling region, the northeastern Pacific off the west coast of North America, where a massive pool of abnormally warm water formed in the mid-2000s, earning the informal nickname the Blob among oceanographers for its distinctive shape on temperature maps. A sprawling patch of red spreading across the satellite imagery like a bruise on the ocean's surface. That marine heat wave persisted for years, visibly affecting regional marine ecosystems, from salmon populations to seabird colonies to the fisheries that depend on both, and became one of the first widely studied examples of a prolonged marine heat wave, a phenomenon later observed across other parts of the world's oceans. Naturally, it's worth mentioning the Mediterranean too, one of the fastest warming enclosed seas on the planet, ringed by coastlines that millions of people call home. Its limited exchange with the open Atlantic makes it especially sensitive to accumulating excess heat, trapping warmth the way a shallow pool heats up faster than the open ocean. And its summer marine heat waves have drawn increasing attention from researchers studying their effects on coastal ecosystems and the intensity of Mediterranean storm systems. Each of these examples isn't an isolated case, disconnected from the others. It's part of a much broader picture of how the planet redistributes the excess energy it's accumulating from a growing radiative imbalance. The ocean, as the primary reservoir of that energy, absorbs it wildly unevenly from place to place, depending on local circulation patterns, depth, wind exposure, and the way each region interacts with the atmosphere above it. Let's return to the satellite data and consider one more important angle: how scientists actually separate a genuine long-term trend from statistical noise in data that's naturally subject to seasonal and year-to-year swings. Picture a graph plotting monthly values of Earth's energy imbalance over the past 25 years. At first glance, it looks like chaotic scatter, bouncing up and down from season to season, spiking after one summer and dipping after the next. But apply statistical smoothing that averages the data over several years, and the trend hidden beneath the noise becomes unmistakably clear. Steady, gradually accelerating growth. That methodology, separating long-term signal from short-term noise, underlies most climate conclusions, and it's exactly why climatologists remain deeply cautious about drawing sweeping conclusions from a single year or two of data, however striking those numbers might look on the evening news. The discovery of this accelerating imbalance mattered not just for what it revealed, but for the fact that it was only possible in the satellite age at all. A reminder that some scientific breakthroughs depend less on a sudden flash of insight than on decades of patient, unglamorous data collection. Before reliable satellite data existed, most understanding of Earth's energy balance rested largely on theoretical calculations and a relatively sparse network of ground-based measurements scattered unevenly across the planet, dense in some regions and almost entirely absent in others, particularly across the open ocean and the poles. The satellite era, which truly began with the launch of CERES in the late 1990s, gave scientists, for the first time in the history of the field, the ability to directly, systematically, and globally measure the exact quantities that determine planetary temperature. How much energy is absorbed and radiated for every region of Earth in every season without gaps. That capability for direct measurement fundamentally changed the nature of climate science itself. Where researchers once had to rely mainly on indirect indicators, shifting air temperatures, melting glaciers, changing bloom dates for plants, the width of tree rings, they now had direct access to the fundamental physical quantity underlying all of those secondary effects. The thing actually driving everything else scientists had been measuring by proxy for generations. So what can we say about the future of measuring Earth's energy balance? Despite some uncertainty tied to the aging of individual satellite instruments, hardware that was never designed to last forever, the international scientific community continues to invest heavily in the next generation of measurement systems. Beyond the already mentioned Libera instrument, set to launch in the coming years as a direct successor to CERES, work continues on new generations of European satellites under the Copernicus program, along with upgraded versions of the Argo float network, including deeper diving models capable of measuring temperature down to nearly 20,000 feet, which will dramatically expand our understanding of processes occurring in the ocean's deepest, least observed layers. Each of these developments is evidence that humanity isn't slowing down in its effort to understand the workings of its own planet, even when the data reveals a picture more complex and less predictable than originally expected. If anything, the complexity seems to be spurring greater investment, not less. Before wrapping up this investigation, it's worth returning one more time to the question that started it all. Why is Earth gradually losing its ability to efficiently send accumulated heat back into space? The answer, pieced together from decades of satellite observation, ocean measurement, and the tireless work of hundreds of researchers spread across dozens of countries, turns out to be more complicated and far more interesting than any simplified picture of global warming would suggest. Earth isn't so much losing its ability to radiate heat as it's gradually losing its ability to reflect incoming solar energy, while simultaneously trapping more outgoing heat due to rising greenhouse gas concentrations. These two processes, running in parallel and reinforcing each other in ways scientists are still working to fully untangle, are exactly what's producing the accelerating energy accumulation that satellites have recorded over the past 2 decades. Recognizing this complexity isn't a reason for alarm. It's an invitation to curiosity. Our planet is far more finely tuned and far more intricate than anyone could have imagined just a few decades ago. Its climate, held in balance by a web of feedbacks connecting a cloud bank over the Pacific to an aerosol regulation written for a city half a world away, to a current of cold water sliding along the ocean floor toward the equator, to a patch of ice 1,000 miles from the nearest human settlement. Every new generation of satellites, every fresh batch of ocean data, every updated climate model brings humanity closer to a fuller understanding of this remarkable mechanism, one that has sustained conditions suitable for life for billions of years on the only inhabited planet we know of in the entire universe. Thanks to satellites, modern models, and new research, scientists are gathering increasingly precise data, but many of these processes are still being unraveled. One measurement, one float, one orbit at a time, and the story is very much still being written.